Hi, my name is Gustavo Cainelli, and I work in the IKT department of IFAC. Today, I will present an evaluation platform for 5G technology in Industry 4.0 scenarios.
Okay, let's start comparing traditional manufacturing with Industry 4.0. Usually, the traditional manufacturing systems have mass production and the amount of products that will be produced are known. This kind of system is not flexible and is static, which means the production system is built to produce a certain kind of product and will produce it until the system is reconfigured, usually by a human. So it is also well engineered. That means that everything is planned in advance, and in some cases, it is planned for the worst case, which leads to a non-efficient use of the resources, as for example, the wireless communication medium. Okay, and now talking about Industry 4.0, the most distinctive features are the flexibility. This means adapting the use of the production system to the needs of the customer without planning every detail of the production system in advance. Moreover, the virtualization, which means some parts of the production system will have virtual copies, and it enables the remote acquisition of information, as well as the observation and control of the environment to save time, reduce amounts of error, and make better decisions. Another characteristic is asynchronous manufacturing, which means that the components in the production flows use auto-identification technology to inform each machine what needs to be done to produce customized products at each step of the production process. And then the system must have self-configuring capabilities. That is, the system must be able to configure itself without human intervention. The machines will not depend on the human elements to be configured. It will be reconfigured dynamically by a digital system, which receives information on how the system is working and controls the production in real time. A crucial part of the highly interconnected Industry 4.0 is the wireless communication system, and especially the 5th generation of mobile network, 5G. 5G has the potential to provide wireless connectivity for a wide range of different use cases and applications in industry. Due to the virtualization of properties and functions of system elements, 5G is gaining further momentum to desired networking in industrial applications, especially non-public networks or 5G campus networks. The non-public networks deployment enables industrial players to have their own networks without depending on a mobile network operator. The core network of a non-public network is rather lean as compared to a public network. And a non-public network can be also deployed for a specific industrial application. For this reason, non-public networks are today the subject of applied research in testbeds and pilots applications. The 5G ACIA is bringing together partners from information and communication technology, ICT, and operation technology to jointly shape 5G industrial domain. And the 5G ACIA has several interesting white papers that address the topic of 5G for industrial application. So as the wireless communication system is one of the key elements of Industry 4.0, and it has to cope with the level of adaptability required by Industry 4.0. It cannot be planned and installed for the worst case. It means that if changes are necessary, the wireless communication system and or its use of the medium should be adapted accordingly. It includes change due to the production process requirements or change due to external disturbances, for example, interferences. Moreover, a wireless communication system brings the possibility of a high number of devices and also mobility, which means that in some cases, the only way to optimize the network configuration process is if the system can adjust itself. So to put wireless communication system in the context of Industry 4.0, self-configuration is required. And for that, collaboration between the production system and the communication system is necessary. To enable this collaboration between the parties, we proposed a digital twin approach. The digital twin can be used to optimize a system even before the installation. In the case of a 5G network, if a digital model can reproduce the behavior of a real network, then it can be used to find the best parameters and optimize the system. And these parameters can be downloaded later in the real plant. In addition, the digital twin is not only used for pre-operation phase, but also for the operation phase. So the digital twin can monitor the system and change its parameters when necessary. The next figure helps us to understand a little bit better. Yeah. So in this figure, we have the digital domain here in blue at the top and the physical domain at the bottom in green. The physical domain contains the production system, the automation system, and the wireless communication system. The digital twin is in the digital domain, here in the blue one. And the digital twins are virtual representations of the assets of the physical domain. In the physical domain, there is data exchange between the assets, and here it's called productive data exchange. For example, a sensor sends its variable to a PLC that uses it to calculate the control action and send a command to an actuator, also using the wireless communication system. The digital twins that are in the digital world can also communicate each other, and here it's called I4.0 data exchange. And the data exchange between the domains, between the digital and the physical domain, is called management data exchange. This management data exchange is used, for example, for the digital twin to reconfigure the system. The digital twin can monitor the current status of the production system or the automation system and can act on that. So for that, the management data exchange is necessary. Each one of these layers can be subdivided in 3 layers. And the first one here at the top is the production system layer, and it includes mechanical parts of the system. The production system is controlled by the distributed automation system in the middle, which uses local automation functions to control the physical system. For example, to set the speed of a motor. And similarly, the distributed automation system relies on a wireless communication system to exchange information between the entities of the automation system. So it is this layer here at the bottom. These three layers are present in the digital world and in the physical world. So there is data exchange between the elements within the same layer and between layers. In the physical domain, it is called productive data exchange, and in the digital domain, it is I4.0 I4.0 data exchange. Yeah. So here we have two use cases of the proposed approach. In this slide, the first one, and in the next slide, the next one. So the first one is called managing the wireless communication system based on production requirements. In this case, the parameters of the wireless communication system will be adjusted based on requirements that comes from the production system or the automation system. For example, if a product has priority, then more communication resources are allocated to the machine that is producing that specific product. So in the figure, we see the three layers of the physical world in green and the digital domain in blue. So the digital domain will have influence on the physical domain. The next one is called movement management based on the quality of communication. In this use case, parameter of a controller that controls an AGV will be adapted based on the quality of the communication. So, for example, if the signal is bad, then the AGV chooses another path or reduces the speed. So in this case, the production system and the automation system are adapted based on the wireless communication system. Okay, now let's talk about the implementation of the digital twin. In the context of the digital twin, the platform INDUSTRIE 4.0 proposed the Asset Administration Shell, or the AAS. The AAS is a concept to implement the digital twin for INDUSTRIE 4.0. The AAS contains information that represents characteristics and behaviors of an entity that here is called assets. And assets are things that are valuable to an organization, and they can be devices, components, machines, documents, or even software. So therefore, the AAS is a tool to create fully versions of any kind of asset in a factory. Through the AAS, an asset becomes an INDUSTRIE 4.0 component. The AAS is composed of a passive part and an active part. The passive part is the properties of the asset which are readable or modifiable. For example, static device configuration, status parameters, and control parameters. On the other hand, the active part consists of procedures and algorithms performed by the AAS. The active part is composed by methods and can be used, for example, to read and write properties values in the AAS or in the asset. Moreover, the active part has decision-making capabilities. So some examples here, we see status assessment, status control, analysis of status history, or negotiation of thresholds and functions, for example. And here again, we have the AAS as the digital twin in the digital world. So we use the color blue, and the asset and the integration model in the physical world. So we have here in green. The assets information is described in the AAS as submodels. And the AAS may incorporate general submodels, for example, identification. Probably all assets have identification data, and also specific submodels, for example, communication. And there is no limit to the number of submodels of an AAS, as they are the level of detail required for the model. Below the submodel level, there are the submodel elements like submodel, like properties, for example. And a property can contain a value that represents parameters of the asset, for example. It can be from several types, like int, integer, bool, or a string, for example. An example is the current status of a pump, let's say on or off, which could be a Boolean value, or for a wireless system, the values of parameters that indicate the status of the radio channel. For example, SINR or SSI. Several tools are available to model the AAS, and platform I4.0 developed the AASX Package Explorer. There is also the well-known automation ML, where you can upload the AAS schemes to model the AAS as you need. And the Siemens solution called Xeon it is also a very useful tool that can be used. In the Xeon, you can upload the OPC-UA companion specification, and the tool generates the node set to XML file, so you can directly use it in the OPC-UA server. Since I am working with the OPC-UA library Open 62541, and I need this node set to XML file, I am currently using the Xeon tool, so I can directly generate my AAS files and use it to build the OPC-UA server. Here we have an example of an AAS of a 5G enabled device. So the 5G enabled device can be any device that can communicate using 5G technology. This includes sensor, actuators, or even more complex system as a machine. In this example, it is an AAS of a machine. So some submodels examples are the identification and localization. Other possible submodels could be related to the machine's functions, for example, bending, drilling, moving, among others. The focus here is in the communication submodel. The communication submodel is responsible for storing all the relevant information related with communication. For that, several submodels and properties within this submodel should be defined to group this information. Currently, within the communication submodel, we have two main submodels, the wireless module and the QoS. The wireless module refers to the characteristics of the 5G communication module itself. So considering datasheet parameters and the current values of parameters. The QoS stores information related to the quality of the service, including the requested values, the assured, and the current values. Other examples could be, for example, to a 5G enabled device, are the SIM card. So here will be aggregated all information related with the SIM card. For example, the IMSI or the PIN. So here we see with more details the two submodels, the wireless module and the QoS. And here we are seeing the submodels in an OPC-UA client viewer. On the left-hand side, we see the wireless module, and this submodule should contain the relevant information related with the wireless module. So the data stored here can be divided into static and dynamic. Static ones are capabilities of the 5G module as delivered. And dynamic ones can be related with the radio channel, as, for example, SINR and so on. So in the QoS, the right-hand side, we see some properties, some characteristics parameters, as, for example, transmission time, update time, and so on. And here we see the required values, the actual values, and the guaranteed values. So we are developing a framework that's composed of the AAS, as we talked before, and also composed of a simulation, a 5G simulation. And the simulation, this simulation model is called SIMU 5G. It is an evolution of a very popular LTE simulator using OMNET. Currently, we are using this simulation in OMNET, but we are checking the possibility for, in the future, to migrate to Zimba. So IFAC would have its own solution for network communication simulation. For this, we had some very productive discussions with Dr. Alex from the Water and Energy team, who is helping us a lot to understand and implement message exchange examples using Zimba. Of course, this is just a first step, but I believe that in the future, IFAC could have its own simulation model for industrial communication networks. This figure shows the general architecture of the framework. It is composed of the digital domain and the physical domain. The physical domain currently is composed of a 5G simulator. And the digital domain contains the AAS. Each AAS has its own asset. And the active parts of the AAS are responsible for exchanging messages with other AAS and also for control the asset. Between the assets in green, there is the productive data exchange. And between the AAS, there is the I4.0 data exchange. Moreover, as I said, there is this management data exchange between the digital domain and the physical domain. So the proposed framework connects the digital domain with a physical domain and can be used to design, validate, and investigate use case for example, resilience, interference, or data analytics. This figure is more a conceptual view, and the next one shows a little more of the implementation view. So here we see parts of the proposed framework. We have two PCs here. On the left-hand side, we see the AAS host, while in the right-hand side, we see the simulator. In the simulation, we see the network elements. There are two machines. Each machine has 5G modules that connect then to the 5G network. The G node B is connected to the UPF and the UPF to the routers. We also have some applications here at the top. On the left-hand side, there is the AAS host. It's basically a PC where the AAS applications are running. Of course, everything could be running on the same PC, but I'm representing here with two different PCs to make clear that we intend to connect our approach to a real network in the future. The idea is to use the simulator now and validate the approach later on a real 5G network. As you know, we have access to 5G network installed in one of the research facilities here at the scientific port, which is a Speicherka. There we can run some tests and with a real 5G network, or with other communication technologies too. As I said before, the simulator can optimize the system even before the installation. So the AAS could keep the best parameters and download it to a real system later. Okay, yeah. In the left-hand side, we see the three AAS, one for each machine, plus the G node B. Of course, it can be extended. Each AAS has an OPC way server. It can that keeps the AAS model specification. And in addition, each AAS is connected to its own asset in the simulation. Also, we have an application called Decision Making Unit. and a visualization unit. The visualization unit is basically a human-machine interface just to show you what the current values of the AES properties are. It can, for example, show the status of the machine, if it's performing some function or not, or how long it will take to be available. Communication information can also be displayed there. So, as the idea of the AES is contain all the information about also the communication system, it's possible to see here in the visualization unit the current status of the radio channel. And the decision-making unit can read and write property values of the AES. So the decision-making unit can store, for example, algorithms that use this data to perform some action on the system. For example, if the channel is bad, it can ask the machines to slow down to avoid problems. Or you can stop one machine and dedicate communication resources to another one. The decision-making unit can also store AI algorithms. As all historical data is kept in the digital twin, this can be used so the system can learn and improve decisions, improve the decision-making. This is a future step that I intend to take together with my colleagues. So yeah, one idea is that the system can learn from events and can improve decision-making over time. Here we see one example of the visualization unit. It's a dashboard developed in the Node-RED framework. As all the assets information are available in the AES, the visualization unit can access it through the OPC way. Here we see some examples of parameters as for example, SINR, which is related with the channel, and QoS information. For example, here the transfer interval, update time, number of received messages. Yeah, of course, this should be extended. This will be extended, but at least it shows that the user can have visual access to the production system. Finally, just as an example, here we have one of the use cases we are implementing. In this use case, each machine has different capabilities and different requirements. This means that each function performed by a machine requires specific communication resources. The machines are connected to the 5G network. And in the proposed scenario, there is a limit of the median use for all machines of 50%. It means that the machines together cannot use the transmission median more than 50% during the execution of the tasks. The table shows the median use of each function, F1, 2, 3, and 4, shows the machines that can perform the functions and what functions are required for each product. So we have two types, product type A and B. The customer terminal generates a new order and forwards it to the machine broker, and the machine broker assigns products to each machine based on functionalities that each product requires. So in this example, 2 orders are generated. The first one, let's call P1, product 1, is an order to produce a product of type A, and the second one, P2, type B. Let's say that P2 has priority over P1, and considering that both arrive at the same time at the machine broker, they will be forwarded to machine 1 and 2. At this moment, machine 1 and 2 start to perform F1. In this case, the median use is 20% only. But then, when they finish, machine 1 starts F2, and machine 2 starts F4, and in this case, the median use is 55%. That means it's beyond the limit. So the decision-making unit will adapt the system to keep the median use under the limit. We can see in this chart, more or less, this behavior. So in blue and green lines are the median use of machine 1 and 2, and in yellow, the sum of both, and in red, the limit. So we see here that when both are performing F1, the sum is below the limit, but when they start to perform F2 and F4, the sum of the two U's are beyond the limit. Then here, it's exceeding the limit, and then the decision-making unit, which is constantly monitoring the network parameters, will act on the production system to put it below the limit. We are currently working on the implementation of this use case and in the simulation, and we hope to have results of this use case soon. Okay, to conclude, today we saw that in the Industry 4.0, the wireless communication system cannot be planned for the worst case. So it has to adapt autonomously to cope with production system requirements or external disturbances, for example. The digital twin approach follows the asset administration shell concept. But for that, the manufacturers of 5G device should provide access to the device parameters. For example, as we see before, SINR and so on. As we discussed before, we are currently using an Omnet simulation to develop our framework, but in parallel, we are working to use also SIMBA in the future. It might be good for IFAC to have its own network simulation solution. We also plan to validate this approach in Speicherka. There we can evaluate the performance of a real 5G system with and without the digital twin approach. And for that, we can use the FTT, which is a framework developed by IFAC to evaluate the communication system from the application point of view. And finally, this work is leading to a work item proposal for platform I4.0, since there are some models templates available there, but not yet for a wireless device. So therefore, what we are doing here can be useful as a submodel template to be used later. Thank you very much, and now we can start our discussion.